Right, we are discussing about chemical bonding, and in that we have introduced the concept of dipole moment. Well, understand that in a covalent bond you have two types of systems, right? The shared pair can be between two atoms which are similar. The shared pair can be between two atoms which are dissimilar. The first one we call it to be a homoatomic system, and the second one we call it to be a heteroatomic system. When we look into the homoatomic system, the bond pair, or I call the shared pair, is exactly at the center. So when I look at the homoatomic system, except for the shared pair at the center and both the atoms who have invested are sharing, there is absolutely nothing to measure in that. Whereas in heteroatomic system, if you actually see, the bond pair is basically unequally shared. As we call it to be a heteroatomic system, it is a bond between two dissimilar atoms. And when I say dissimilar atoms, if you recollect, if you have 130 elements in the periodic table, then if you ask me what is the single point difference between the 130 elements in the periodic table, then I would like to say it is basically nothing but size. So out of these two atoms which are dissimilar, participating in covalent bond, one of the atoms will be smaller. And we all know that smaller atoms will be having greater electronegativity generally, right? So they do possess greater electronegativity. So in that case, then the shared pair is unequally distributed between the two atoms which are dissimilar. Then what happens is this bond pair is towards that atom which is actually smaller. And in that process, partial negative charge and a partial positive charge is visible, quite visible on the bond. So basically what I'm telling in is heteroatomic system in a covalent bond, poles are developed. So when the poles are developed, one thing we can get inference from this is basically understand if someone is asking us that what is a 100% covalent bond, then I would like to say 100% covalent bond is that where the bond pair is exactly at the center, equally shared, and it is 100% covalent bond that is formed between two nonmetals. So if you have equal sharing of the bond pair between two atoms participating in covalent bond, we call that to be 100% covalent bond. Now the issue arises if the bond pair is unequally shared, not at the center, and it is actually biased towards one of the atoms which is smaller, then we say some percentage of ionic character is induced. You must understand that, right? So that means that ionic character is induced, but the bond remains to be covalent. The bond remains to be covalent for the simple reason the bond pair which is biased towards or shifting towards the atom which is smaller in size, that means that the atoms are not leaving the shell or the other atom is not gaining the electron. If that was true, then it is 100% ionic bond. You are not leaving the shell. In ionic bond, what happens is the electron is kicked out of the shell and the other atom is actually eating away the electron to get what? The negative charge. In this case, there is absolutely a shift of what? Electrons from the center point to that atom which is actually smaller in size. You must understand that, right? So a degree of ionic character is induced into the covalent bond, but the bond remains to be what? Covalent, and it is never ionic unless the electrons are kicked out from the shells. And in this case, we call this to be a polar covalent bond maximum. We call this to be a polar covalent bond, but never what? Ionic bond. You must understand, for the simple reason the poles are the charges that are developed on these atoms due to unequal sharing possess partial charges. They don't contain full charges. If it was full, we call that to be an ionic bond. Maximum what you can call is a polar covalent bond. That means that it has polarity in a covalent bond. Now what is polarity? Unequal sharing of what? Bond pair. You must understand that, right? So there is something happening in what? Heteroatomic system. We don't find absolutely anything in homoatomic system, and we consider that to be a 100% covalent bond and the polarity is 0. In case of heteroatomic system, the bond pair shifting towards one of the atoms and poles developing, and there is polarity in the bond, then I think I'm prompted to do something. I'm prompted to measure something, right? The degree of polarity. Because are you shifted too much? Are you shifted, 80%, 90%? How much is the percentage of ionic character? How much is the polarity in the bond? There seem to be something is prompting to us to check out how much is the polarity in the bond. Is there anything to measure, right? These all things crop up in what? Polar covalent bond, which is there in the heteroatomic system. Now look into this. If I consider a heteroatomic system, that means a bond between A and B, and suppose if B is smaller, this bond pair is shifting towards B, and this develops a partial negative charge, and this develops a partial positive charge. That means that the electrons of A are not leaving its shell, and the B is absolutely not gaining any electron. There is only a shift of these electrons towards B because B has greater electronegativity, and this unequal sharing is called polarity, and such a covalent bond is called polar covalent bond. You must understand. So when poles are developed, there is something to measure in it. Watch carefully here. Since the bond pair is shifted towards one atom, then I think that the direction is actually fixed towards that atom which is more electronegative. When the direction is fixed, then it seems to be absolutely a vector, which is shown like this. Watch. Right, it is shifting towards B, and the tail possessing a positive charge, this charge which I am referring to. So this seems to be a vector because the direction of the pull or the tendency to attract electrons towards one atom which is more electronegative is actually fixed. Hence, I call this to be polarity which is present in a bond seem to be a vector quantity which is represented by that vector symbol with the tail having a positive. So you must understand that, right? So what is there to measure in this? One thing you must understand, this is a partial charge, it's not a full charge. In case AB was ionic, it is hypothetical, it can never be what? AB was ionic. In case, it will never be. Hypothetically or theoretically, understand that if AB was ionic, then this would have given us A plus and B minus. You can actually see these are full charges. And this unit positive charge or unit negative charge has an E value which is equal to 4.8 into 10 power minus 10 electrostatic units. That is the unit of charge in CGS system, you must understand. Assuming that the AB is what? Ionic, then it can never be ionic. We are discussing actually covalent bond. Max you can label it as be polar covalent bond, but you can never be what? Ionic. We call that to be polar covalent bond, right? We are just having an assumption that in case AB was ionic, then you have a unit positive charge or unit negative charge whose value is 4.8 into 10 power minus 10 ESU. You must understand that, right? If that is the case, remember these charges which you are seeing are partial charges. So when they are partial, their values are lesser than this. You must understand. In fact, these values are fraction of this. You must understand, right? So these values are partial charges, and partial charges are fraction of the full charges. You must understand, right? That's why I still label that to be a polar covalent bond, a bond with some degree of what? Ionic character. You must understand that, right? If this is the case, then there is something to measure. So what I will do, let the charge developed, let it be E. Let the charge developed be E, right? And let the distance between poles is D. then mu is equal to E into D. You must understand. Mu is E into D. The product of E and D is nothing but mu, where mu is called a dipole moment. And let me tell you that this dipole moment represented by mu is basically a vector quantity. It's basically a vector quantity, you must understand. So the mu is a vector quantity. This is how it is determined, and the pointer is towards that atom which is actually smaller, normally more electronegative. You must understand that, right? So that is about the dipole moment. All this is cropped up because we are dealing with a heteroatomic system in which one of the atoms is smaller or electronegative, I may call. So these electrons are biased towards B, but remember that these electrons are still there with E. You can actually see these are the two electrons invested by A and B. This electron, even though is shifted towards B, it is not leaving the shell of A. It is not leaving the shell of A at all. It still remains with A. Nor B is gaining a total what? Electron. You must understand that. So I call that to be a partial positive and partial negative. And if it is fully leaving it, then it's called an ionic bond, and unit positive charge will have this much value in CGS systems, and these are actually fractional of that. You must understand that, right? If that is a dipole moment, then I think we have issues with communication, because you can't use your hand gestures to tell us how much is the dipole moment. You can't tell me that I have this much dipole moment, I have that much dipole moment, in my house I have this much bond, this much is the dipole moment. No, you can't gesture like that. So we have some units to actually communicate with that. And how do we actually get into the units of dipole moment? Watch carefully here. How do we actually arrive at the units of dipole moment? Units of dipole moment, how do we arrive at? How do we calculate this? Now, since you said the equation is mu is equal to E into D, let us take E value to be 10 power minus 10 ESU. I'm assuming it. It's basically just assume. That is purely an assumption. No experimental backing, just assume E value to be 10 power minus 10 ESU, and the D value is 10 power minus 8 centimeters. People might ask me, why did you take 10 power minus 10 ESU? Why are you not taking the other values? Then understand that 10 power minus 10, you can take any value less than the 4.8 into 10 power minus 10, which is the total unit positive charge. You can actually assume any value, no one will hang you. But the value must be a fraction of the total unit positive charge. And the total unit positive charge is 4.8 into 10 power minus 10 ESU. And I have taken less than that. So that is E is this much. You can take your value, but it will be a different unit. For if you wanted to have a Debye unit for dipole moment, then E must be this much and D must be this much. Then I think if you actually see, then if you substitute mu is equal to 10 power minus 10 into 10 power minus 8 ESU into centimeters, this mu is 10 power minus 18 ESU into centimeters. This is what is called 1 Debye. This is what is called a Debye. So the units of dipole moments are basically what? Debyes. You must understand. And 1 Debye value is 10 power minus 18 ESU into centimeters. You must understand that is how we derive it. Now remember that why did I take 10 power minus 10? You can take any value, but that will be your personal unit. No one will actually hang you. But if you wanted 1 Debye, which is universally accepted for communication, then I think you must be taking E value to be 10 power minus 10 and D value to be 10 power minus 8 and substitute. Then you get 10 power minus 18 into ESU into centimeters. That's how 1 Debye is defined. You must understand that, right? All this discussion is cropped up for the simple reason we have taken heteroatomic system. And heteroatomic system, once you take it, polarity is induced. Polarity is induced, some percentage of ionic character also gets induced. If some percentage of ionic character gets induced, then It's not an ionic bond. It's not an ionic bond. Max, I can label it to be a polar covalent bond, where you have polarity. What is polarity? Unequal sharing of bond pair. This is what maximum you can say. You must understand that, right? And are there anything to measure? Yeah, we have something to measure because the charges are developed. So let the charge be E. Distance between AB, which is otherwise called bond length, is D. Then the product of E into D is mu, which is called the dipole moment, which is a vector quantity. Which is a vector quantity shown this way. Right, that is how it is. And if you wanted the units of dipole moment, one unit of dipole moment is dBs, and 1 dBi is 10 power minus 18 ESU into centimeters. And if you wanted to know how you got this, then you assume an E value which is lesser than the total positive charge and D value which is 10 power minus 8, and we call it to be dBi. Anything you can take it, but lesser than the unit positive charge, that will be your personal unit. But 1 dBi is 10 power minus 18 ESU into centimeters is the language which we'll be using for communicating what? Dipole moment between molecules. You must understand that, right? If this is the case, let us take some applications of dipole moment which will be asked in the exam. Watch carefully here. Watch. Let us actually go in for some of the applications of dipole moment. And I am writing a statement in inverted commas. Watch carefully here. Watch carefully here. Watch carefully. Applications of dipole moment. Applications of dipole moment. What are the applications of dipole moment? Number one. Remember, dipole moment is a vector quantity. It's basically a vector quantity and denoted by a vector this way, and you have a positive charge on the tail. Right? Now, what are the applications of what? Dipole moment. Number one, what I'm telling is, if the dipole moment, or otherwise I can simply say, or otherwise I can put it in inverted commas and say, even though, look into this, even though, right? Even though, look into this application number one, right? Since you said dipole moment is a vector quantity, shown this way, this is the vector, I write a statement. Even though bonds are polar, now you must understand what is polar. Polar is basically unequal sharing of bond pair. So what he is basically telling that even though the bonds are polar, but still sometimes net dipole moment, that is mu, is zero. Sometimes it is zero. You must understand. Even though the bonds are polar, but still sometimes the net dipole moment will be zero. You must understand. So a molecule can be having 2 bonds, 3 bonds, 4 bonds, 5 bonds, 6 bonds, 7 bonds. But what is happening is the bonds are polar. That means that in all the bonds which you are referring now, the bond pair is unequally shared. But still sometimes what happens is the net dipole moment might come to zero, and this we can explain only when you assume that the dipole moment is a vector quantity, right? For example, if I take one example here, look into this. This is carbon dioxide. This is carbon dioxide molecule. And we all very much know that the oxygen is more electronegative than carbon, because oxygen is in the 6th group, right? It belongs to the 6th group, and carbon is belonging to the 4th group. And when we move from left to right, the electronegativity increases. You must understand. So if oxygen is more electronegative, let me point out the dipole moment vector now. So that means that these bond pairs which are present here are basically pulled by this oxygen. So this is the dipole moment which is mu1, right? That is one of the dipole moments, mu1. And what I'm showing here is basically I'm telling you that the bond pairs which are supposed to be at the center are actually pulled by what? Oxygen, you must understand, are pulled by oxygen. And it develops partial double negative charge. You must understand. Because you have a partial negative here, so you have get partial double negative here, right? So this bond, these bonds are absolutely polar. This is polar, meaning that you have unequal sharing in this bond because the bond pair is now towards oxygen, which is supposed to be at the center. So you have polarity. So this bond seems to be polar covalent bond, and you can see here this bond is polar with an unequal sharing. And that's why I say let the dipole moment, the vector be pointed towards oxygen this way. Similarly, you can have these bond pairs pulled towards oxygen with a partial double negative. Since it is pulling, you can actually see the vector pointing out this side with the tail showing positive. You must understand that. You must understand that, right? The carbon is now becoming electron deficient because the electrons are pulled over by both the oxygens. So what this statement is basically telling you is, even though the bonds are polar, now look into the bonds are polar or not. This bond is polar and this bond is also polar, where you have unequal sharing. So these two bonds are basically polar. So it says even though bonds are polar, but still the net dipole moment sometimes is zero. So what it is basically telling is you can apply your concept of vectors, right? The resultant of this and the resultant of this ultimately gets cancelled because these two are vectors. These two are vectors equal in magnitude. Equal in magnitude, of course they are equal in magnitude because this bond is same as this bond. You don't have two dissimilar atoms, both are oxygens. So vectors, right, equal in what? Magnitude, but opposite in direction. But opposite in direction, you can simply say opposite in direction. Then if they are opposite in direction, they cancel each other. So they absolutely cancel. So the mu net dipole moment is zero. Net dipole moment is zero. This is mu1 and this is also mu1. It's not mu2. You can't call it mu2. It is mu1 because it is both the CO bonds. They are similar. So even though, that's why I said vectors equal in magnitude but opposite in what? Direction. They both cancel each other and the net mu is equal to what? Zero, you must understand. So I'm asking you, don't celebrate when you see polar bonds. It is not the question of celebrating because sometimes net dipole moment might be zero. Like you see here, this is a polar bond, that's a polar bond. So you cannot say that the molecule as a whole is polar because you have two vectors pointing out in two different directions with the same magnitude. So the net dipole moment or the mu resultant will become sometimes zero. Now you might ask me, so what? You might ask me, so what? If that is the case, then there is something to understand here, right? And I would like to highlight this. And I would like to highlight and draw the attention of the students. Look here. If the net dipole moment, watch carefully here. If the net dipole moment is zero, then such molecules are said to be symmetric. You must understand, they're said to be what? Symmetric molecules. So when you're reading a textbook or a reference book back home, when you come across the molecules seem to be symmetric, then you must understand that the net dipole moment of such molecules will come to 0, even though you have n number of bonds in them and all the bonds are polar, unequal sharing of bond pairs, but still if the net dipole moment is 0, then we call such molecules to be symmetric. You must understand. Right? Well, let us extrapolate and understand better. But before that, before I go there, understand that dipole moment is a vector quantity. And what I'm writing is, even though bonds are polar, but still sometimes the net dipole moment comes to 0. You can see here this bond is polar, this bond is polar. So here is a vector mu1, here is also a vector mu1, same vectors, but they are equal in magnitude but opposite in direction. So net dipole moment is 0. Then I would like to call, and I want to label this, and I'm labeling this. So this molecule carbon dioxide is basically what? Symmetric. So I call what? I call carbon dioxide molecule to be what? Symmetric. You must understand that. Cut it off. Right. So let us write it properly. Like, what do you mean by this? Watch carefully. What I meant is absolutely this. Look into this. Look into this. To judge whether a molecule is symmetrical or not. Symmetrical or not. Right? To judge whether a molecule is symmetrical or not, that is one of the questions which will be asked in the exam. Symmetrical or not, then use the dipole moment. Then I would like to say, if mu is 0, if mu, the net mu of the molecule, total molecule, the dipole moment of a molecule is 0, then such molecules are said to be symmetric. Then such molecules are said to be what? Symmetrical. Right? That is the theoretical part. Now, if you wanted to get into some details of this, what do you mean by this? Which molecules shall be symmetrical and which molecules will be having such dipole moments to be 0? Let us take few more examples for better understanding. Look into this. So what I said, if a molecule is symmetrical or not, if you wanted to judge it, how do we judge it? How do we judge? Then if mu is 0, for a molecule, then it is what? Symmetrical. You must understand that, right? Let's take few examples. Look into this. Let us take the case of BCl3. This is BCl3. This is triangular planar, rather. This is triangular planar. You must understand, this is triangular planar, right? And now what we are doing, if you see, you have 3 bonds, and all the 3 bonds are polar. All the 3 bonds are polar. Polar means you have unequal sharing of bond pair. Now this will be shifted here. So if I can draw the vector, this is the vector, that is the dipole moment. You must understand. And if I call this the dipole moment to be mu1, right? And if you see, this is what is mu2. This is also mu1, no mu2s, because the bonds are same. So you have 2 vectors, right? 2 vectors. Now let us actually deal with these 2 vectors now. And you have the 3rd vector. This is also what? Mu1, because the bonds are same. Now how do we analyze as a mathematics student is, I say this is polar, this is polar, this is polar. All the 3 bonds are polar. All the 3 bonds are polar, but sometimes net dipole moment would be 0. Like for example, the resultant of these 2 vectors, the resultant of this and this is a vector, is a 3rd vector. This is the mu resultant. This is the mu resultant. You must understand, it is a mu resultant and it is pointing towards that way. And now if you see, the resultant of any 2 vectors, not only this is the case, this and this, you have this way. So I can simply say, I can write like this. The resultant of any two vectors, it is up to you. You can take these two or to these two, then the resultant will be this way, or these two, then the resultant will be these two. So you should understand the resultant of any two vectors is a third vector. The resultant of these two is a third vector. This is the mu resultant, third vector, which is equal in magnitude, but opposite in direction to the third vector. You must understand. You can actually see the resultant of these two vectors, this vector and this vector and this vector are equal in magnitude but opposite in direction. This is opposite in direction, this way and this way. So what I say is basically, even though the bonds are polar, the net dipole moment is zero. You must understand. So the net dipole moment is basically what? Zero. You must understand. So I am basically asking you, don't celebrate. Please do not celebrate. Just because the bonds are polar, you don't celebrate. Even though the bonds are polar, sometimes the net dipole moment comes to what? Zero. You must understand. And such molecules are said to be symmetric. So I call this to be a symmetrical molecule. You must understand this. This is a symmetrical molecule. So just understand, the resultant of any two vectors is a third vector which is equal and opposite in direction to the third vector. You must understand this. So net dipole moment sometimes comes to what? Zero. You must understand this. Well, I give you another example for you. Watch. You see here, this is carbon tetrachloride. This is the carbon tetrachloride. You watch. You have 4 bonds. And all the 4 bonds are polar. All the 4 bonds are polar. You can actually see. When all are polar, let's point out the vectors. This is vector 1. This is vector 2. This is vector 3. And this is vector 4. You must understand. Right? This is the vectors. Those are the dipole moments. And what you do is the resultant of these two vectors is a vector like this. That is the mu resultant. And the resultant of these two is another vector. This is the mu resultant. And this vector gets cancelled because they are opposite in direction and equal in magnitude. So now we have here polar bond, polar bond, polar bond, polar bond, unequal sharing of what? Bond pairs. But still, the net dipole moment, if you actually see, it is again coming to what? Zero. And such molecules are said to be what? Symmetrical. So the carbon tetrachloride is also what? Symmetrical. You must understand this. Like, for example, you can actually take beryllium chloride. This is the vector. This is the vector. So again the net dipole moment is coming to what? Zero. Then also I say that the beryllium chloride is basically what? A symmetrical molecule. You must understand. You must understand that. Right? So let us fix it off. After understanding what I am telling, let us fix them. Let us fix them. When I say fix them, let us understand and carry it forward for the exam. So there will be questions on that. There will be questions on that. Watch carefully here. Watch. Let us fix these symmetrical molecules. Let us fix them off for our better understanding to write the exam. Right, let us see. We are discussing applications of dipole moment. And look into this. Let us fix. Let us actually fix symmetrical structures Symmetrical structures, I'm referring to what? The molecules. Now I write the symmetrical structures for you, then we will have something in common because we are writing them as a group. When you're writing them as a group, there should be some basis for making a group, right? So look into the structures, you will get it. For example, say this. I have beryllium chloride, which is undergoing sp hybridization, and the shape is basically linear. The shape is basically what? Linear. Then I have boron trichloride, whose hybridization is sp2, and this is triangular planar. Triangular planar, you must understand. Similarly, you have carbon tetrachloride, which is sp3, and this is tetrahedral in shape. Similarly, you have PCl5, which has an hybridization of sp3d, and this is having trigonal bipyramidal. And you have your SF6, which is having sp3d2, which is having octahedral. And even I have IF7, which is having sp3d cube, which is pentagonal bipyramidal. Now there is something common in all this. There is absolutely something common in all this, in all these structures, right? What is common in all this is, here the mu is 0. The mu is 0. And remember, the mu is 0. Mu is 0. And the mu is 0. And the mu is 0. Mu is 0. So the dipole moment of this, and this is absolutely 0. Absolutely 0. And I said we will fix it off in a better way. In a better way, we can fix it off. That is, how to fix it off is, in all these molecules, in all the molecules, in all these molecular structures, in all these molecular structures, central atom, the central atom has 0 lone pairs. 0 lone pairs. So all these have bond pairs. It has 2 bond pairs, 3 bond pairs, 4 bond pairs, 5 bond pairs, 6 bond pairs, 7 bond pairs. It has 0 lone pairs. 0 lone pairs. And when you have 0 lone pairs, I call all these to be, all these structures you have listed out, all these structures which you have listed it out, all these structures so-called linear, triangular planar, tetrahedral, trigonal bipyramidal, octahedral, pentagonal bipyramidal, they are all what? Symmetrical structures. You must understand. Symmetrical structures, you must understand that. So simply speaking, a student can grasp much easily, understand and remember very easily. If the central atom has no lone pairs, then we say such structures are symmetrical structures. And the dipole moment will be 0. And the dipole moment will be 0, you must understand. And the dipole moment is 0. When is the dipole moment 0? When the central atom doesn't have a lone pair, it is having only bond pairs. So the structures, linear, tetrahedral, pentagonal bipyramidal, trigonal bipyramidal, tetrahedral, square planar, triangular planar, all these are what? all these are having zero lone pairs, and all these structures are said to be symmetrical with a dipole moment equal to 0. Dipole moment equal to 0. So if the dipole moment is equal to 0, then I think we brand that molecules to be symmetrical molecules, you must understand. We brand such molecules to be what? Symmetrical molecules, you must understand that. Right? On the other hand, so I think I'm clear. I'm actually very clear. So I would like to underline before I get into the other thing that, in all these molecular structures, the central atom has zero lone pairs. No one will be having a lone pair at all in all this. So such structures predicted by the hybridization, they are exactly predicted by the hybridization. There is observed, and the real structures will be the same, and the bond angles are also same, and such structures will have net dipole moment equal to 0, and thereby we call these structures to be symmetrical. We call the structures to be what? Absolutely symmetrical. On the other hand, watch carefully here. If the central atom, now what is a central atom in which hybridization is taking place? If the central atom has lone pairs on it, if the central atom has lone pairs on it, then we get distorted structures. Then we get distorted structures. When I say distorted structures, then the mu resultant of the molecule is not equal to 0. You must understand. Then the mu is not equal to what? 0, you must understand. The mu is not equal to 0, you must understand. And suppose if the mu is 0, then we get regular structures. When you have regular structures, they call them to be, the molecule is what? Symmetrical molecule. The molecules are said to be what? Symmetrical molecules. On the other hand, if the mu is not equal to 0, then you get distorted structures. Then the molecules are said to be unsymmetrical molecules. Then we call this to be what? Unsymmetrical molecules, you must understand. Then in such case, the mu's resultant will prevail. There is absolutely no other vector to cancel it. There will be mu resultant that is acting in the molecule, and such molecules that will be having a distorted shapes are called to be unsymmetrical molecules. For example, look here. For example, take the case of water. Take the simple case of water molecule. This is water. That is water. And then let the bond angle be theta. Let the bond angle be what? Theta. And remember, right, if I point out the vector here, this is where the oxygen is pulling. So this is mu1. That is a vector mu1. And you can actually see this way, that is also mu1 because the vectors are same, because the bonds are same. Then you will have a resultant vector going this way. This will be the mu resultant. And this will prevail. And this will prevail because there is no other vector to cancel it. That will prevail. Right? And how to calculate this? This is mu resultant. The mu resultant can be calculated. Square root of p square plus q square plus 2pq cos theta. You must understand. P square plus q square plus 2pq cos theta. In this case, mu r is equal to mu1 square plus mu2 square plus 2 mu1 square cos theta. This is the mu resultant, and there is absolutely no one to cancel. You don't have a cancelling vector. So the mu resultant will prevail. So the net dipole moment is not equal to 0. And this structure, this molecule is said to be unsymmetrical molecule. You must understand. This is said to be what? Unsymmetrical molecule, you must understand. So you have a resultant vector which is found out in physics. You were told that p square plus q square plus 2pq cos theta. You must understand that. So that mu r is not cancelled by any other vector that is available. So the mu r will prevail. So now what we will do, we'll fix it off. As we have fixed the symmetrical molecules, let us fix an unsymmetrical molecule such that you can apply that in the exam, right? Let us take and fix it off. Observe. Observe. Let us fix it. Let's take these examples. The unsymmetrical structures. The unsymmetrical molecules with distorted structures where the dipole moment is basically not equal to 0. Well, I give some examples. Watch carefully here. I write few. Water. Water. I write ammonia. I write pH3. I write XCF2. I write XCF4. I write XCF6. And I write even ClF3. All these molecules. Well, I have placed all these at one place, indicating that there is something common in all this. What is common in all this? Let's rewrite properly, please. Let's rewrite properly. ClF3, this is an interhalogen compound. Then you have ammonia. Then you have pH3. You have water. You have H2S. You have XCF2, XCF4, and XCF6. You don't have XCF7. Right? So these are all the molecules. What is common in all this? Let me check out. Let me check out. Now, what are its structures first? This has a T shape. This has pyramidal. This also has pyramidal. This is angular. This is also angular. This is basically linear. This is square planar. And this is XCF6 is basically, let me write only few, XCF6, which is having distorted octahedral. Right? So you have all these molecules. And remember, all these, I consider them to be possessing distorted shapes. They all are distorted shapes. They all are called to be distorted shapes. They are not regular shapes. They are all distorted shapes or structures. Right? And remember, for all these distorted shapes, for all these, the mu not equal to 0. The mu, the dipole moment, is not equal to 0. Mu not equal to 0. Not equal to 0. So in fact, I can say for all distorted shapes, the mu is basically not equal to 0. You must understand. Now, as I said, we will fix it off. So let us fix it off. How to fix it? You see here, this chlorine belongs to 7th group. 7th. So that means that you have 7 electrons in your pocket. 3 you invested. 3 you invested. So you are still left with 4. That means that this has 2 lone pairs. Those have what? 2 lone pairs. You must understand. Look at this. Nitrogen has 5 electrons in its outermost shell and it has invested 3. So you have 1 lone pair. Must understand. Similarly, pH3 will be having 1 lone pair. Water, it belongs to, oxygen belongs to 6th group. So you have 6. 2 you invested. So you have 2 lone pairs. And you see in H2S, it has 2 lone pairs. And in HCF6, xenon belongs to 8th group. So you have total 8 electrons. 8. And you invested 6. Invested 6. So you have 1 lone pair. So I can simply say you have 1 lone pair. And we were told whenever, I want to fix it off. I wanted to fix it off now. Whenever a central atom has lone pairs. Whenever the central atom has what? Lone pairs, the structure is basically distorted. Then for all distorted structures, the mu value is not equal to 0. Then we call such structure or molecules to be unsymmetrical molecules. You must understand. Unsymmetrical molecules, you must understand this. Unsymmetrical molecules, you must understand. Right? So unsymmetrical molecules, you must understand. That means that the T shape is unsymmetrical, pyramidal is unsymmetrical, pyramidal is unsymmetrical. So ammonia, pH3, H2O, H2S, XCF6, all these are unsymmetrical molecules because you have a prevailing resultant dipole moment which is not cancelled as in the case of what? Symmetrical molecules. You must understand this. Right? So let us finally write down something. So it is as simple as that. Please look into this. Molecules symmetrical or unsymmetrical. Molecules symmetrical or what? Unsymmetrical depends on presence of lone pairs. So, lone pairs 0. So, the net dipole moment is also 0. Then you will have regular structures. Then you have what? Regular structures, and such molecules are said to be symmetrical, you must understand. And now suppose if the lone pairs are not equal to 0, right? Then if the lone pairs are, I withdraw what I am telling. Mu is 0, right? Mu net is what? 0. If the lone pairs are 0, then the net dipole moment will be 0, and you have regular structures, and such molecules are said to be symmetrical. If lone pairs are not equal to 0, then mu also not equal to 0, you must understand. Then you have not regular structures, then you have distorted structures. Then we say such molecules to be unsymmetrical, you must understand that. Right? So that is how the application number 1. Let us take some of the organic compound examples to explain further and understand better. Right? So understand that we are still in dipole moment. That means we are still hanging on toward covalent bond, but we are discussing polar covalent bond. That means unequal sharing of the shared pair.